All right, we are going to look at the method of initial rates. And in the method of initial rates, we can use a set of data for a reaction. And on our reaction here, 2 moles of nitrogen monoxide react with 1 mole of oxygen gas to give 2 moles of dinitrogen monoxide. We can run the reaction several times, manipulating the starting reactant concentrations, which are going to be here and here. And as we do that, the initial reaction rate, which is in the final column, changes. And as we would expect, if we look at experiments 1 through 3 example, as the oxygen is increased, the reaction rate gets faster. And if we look at experiments 4 and 5, or 3 through 5, as the nitrogen monoxide rate increases, the reaction rate gets faster. So as we go from experiments 1 down to 5, as we increase the reaction rate, or excuse me, as we increase the reactant concentrations, the reaction rate goes faster. And the rate is in the final column here. So, generally, if we want to determine a rate law for a reaction like this, my reactants in the equation are nitrogen monoxide and O2. So the rate law is going to have the form of rate equals K, which is the rate constant, times NO, nitrogen monoxide, times O2, nitrogen dioxide. And these are going to be to some power that we call the orders. I'm just going to call them A and B for now, because we can't know the orders without experimental data like we have in the 5 experiments up here. So at this point, now we can use these experiments to determine these orders. If we look at experiments 1 through 3, you might notice that my NO is held constant. It is not changed. It is 0.001 moles per liter in all 3 of those experiments. But my O2 concentration changes. So these experiments can be used to determine the effect of O2 on the rate. If we look at experiments 3 through 5, the opposite is true. For 3 through 5, the O2 is constant and the NO changes. So that will let us determine the effect of the NO on the rate, okay? And so typically in class, when you get a set of reactions like this, we're not in the laboratory and we give you an idealized case. So these are all going to fit right on a line very nicely. The data will be fairly much free of error. So you can pick any 2 of these experiments. So if I want to determine the effect of O2, that means I want to get the order B. So I can use these to determine the order B, and I can use these experiments to determine the order A. And when I was talking about the data being kind of perfect in an ideal made-up supply problem like this, I mean you can use any two of these experiments. So I'm going to start by using experiments 1 and 2, okay? If I look at experiments 1 and 2, I notice that as the NO is held constant, the O2 is doubled from 0.001 to 0.002. And if I look at the rate goes from 7 times 10 to the negative 6th to 1.4 times 10 to the negative 5. So the rate also doubles. Okay? So as my O2 doubles, the rate doubles. Now, let's take a look at this rate law for a moment. And I see that this rate gets 2 times greater while this stays the same, and this gets 2 times greater. Now, this is a rate constant, and by the definition of rate constant, it means that it stays the same also. So, as O2 doubles, my rate also doubles. That tells me that B must equal 1. Okay? B, or the order in O2, must equal 1. So now I can rewrite my rate law, knowing what I know at this point. Now I know that it's going to be rate equals K NO to the A power O2 to the first power, but do we usually write the first power? Usually we don't. I can just leave that blank. Okay. So now I've determined one of my orders. Now I want to determine my next order, which is A. So now I can use any two of these two, and so I'm just going to use 3 and 4. If I use experiments 3 and 4, I notice my O2 stays the same. It's 0.003. My NO doubles from 0.001 to 0.002. And what happens to my rate? My rate goes from 2.1 to 8.4 times 10 to the negative 5th. 2.1 to 8.4. That's an increase of 4 times. So my rate gets 4 times larger. When I double my NO, my rate is going to get 4 times larger. So let's look at this for a second. My rate gets 4 times larger. Again, this is a constant. My O2 stays the same now, so it's staying constant. My NO gets 2 times greater. If this doubles, but this gets 4 times greater, this A must be an order of 2 because 2 squared gives me my 4. So this means that my order A is equal to 2. So at that point then, that means that I can rewrite my rate law in its final form of rate equals K in O squared O2 to the first power. That is going to be my rate law. I have now determined my orders. Okay. Now, let's say that I wanted to next determine the value of my rate constant, K. If we had real laboratory data that wasn't perfect, we would probably want to use all of these data points. But in the ones you're typically given in class, we can use any of these 5 data points and substitute in. So I'm going to just use the data in experiment 1. So from experiment 1, I have my NO and my O2 molarities are both 0.001. Or in other words, 10 to the negative 3. Either one of both of those are 10 to the negative 3. Those are given, okay? My rate is 7 times 10 to the negative 6th for experiment 1. I can now use that to solve for K. Now we're also going to have units in here. So my units are going to be moles per liter. And we could do it in moles per liter, but it might be easier to do it in molarity. So this is going to be a unit of molarity. This is going to be a unit of molarity also, right? And my rate is in moles per liter second, or in other words, molarity per second, okay? So I'm going to rewrite this to solve for K. My rate is 7 times 10 to the negative 6th molarity per second. That equals K. And then this is going to be 10 to the negative 3 molar squared. And this is going to be 10 to the negative 3 molar. I can divide both sides by 10 to the negative 3 molar squared, 10 to the negative 3 molar. And I will get my K. Now, if I cancel some units here, I can see that that molar is going to cancel with that molar. And then if I do the math to divide that, I'm going to get 7 times 10 to the third. I'm going to have a molarity squared in the denominator. Make a little room for my units here. And so I could call that molarity to the negative 2. And I'm going to have a seconds in the denominator, which I could call a second to the negative 1. That is going to be my K. I could also write that as 7,000 if I wanted. My molarity to the negative 2, I could also write as liters squared per mole squared. My s to the negative 1 would be seconds in the denominator. So that's another way I could write K. Either one of those would be acceptable. So that's how I would determine the rate law. So my rate constant K and either of those would be that form right there. And I should be able to get this same result for K using any of those other 4 sets of experimental data also. So that's how you determine a rate law using the method of initial rates.